All right, guys. So far we've done quite a bit of stuff with complex numbers, but we really haven't seen anything that's very, very useful or cool yet. I want to go through an example of an application of complex numbers that convinced me that complex numbers were extremely useful. I'm sure that everyone kind of suffered when they went through trigonometry and they talked about the sum of the angles formula for both sine and cosine. The formulas that are obtained are really large formulas, but by using complex numbers, they kind of come out of the algebra very naturally, and that's the one thing that I actually wanted to focus on. So this is complex numbers a cool application. The first thing that I want to do is want to talk about when it is it that we say that two complex numbers are equal to one another. So this is a definition. This is the definition of equality. So suppose that you have two complex numbers, z1, which has the Cartesian coordinates x1, y1, and z2, which has the Cartesian coordinates x2, y2. And they can have polar coordinates as well, but Cartesian is enough. Then we say that x1 or z1 and z2 will be the same if and only if the real part of one complex number is equal to the real part of the other, and the imaginary part of the complex number is equal to the imaginary part of the other. So here, these two are equal if x1 is equal to x1, y1, x1 is equal to x2, y1 is equal to y2. You'll see where this comes into play here in a second. So suppose that we had two complex numbers in polar coordinates. So suppose that we had z1 is equal to e to the j alpha, and z2 is equal to e to the j beta. So these are written in polar coordinates, right? On top of that, the magnitude of both of these is the same. Right? Now, what I want you to do is to consider the product of the two. So I'm going to take a look at z1 times z2. So I can take e to the j alpha times e to the j beta, and I can actually combine what's in the argument like so. Now, this happens to be in polar coordinates. I can also rewrite each one of these in Cartesian coordinates. So e to the j alpha is also cosine alpha plus j sine alpha. And e to the j beta is also cosine beta plus j sine beta. And on the opposite side, right, this portion right here can be rewritten as, well, it's the cosine of the argument alpha plus beta plus j times sine alpha plus beta. So all I did was I rewrote this part in Cartesian, I rewrote this part in Cartesian, and I rewrote this part in Cartesian. Right? Now, on the right-hand side of this equation, there's nothing left to do. But over here, I can actually FOIL. Right? So if I take cosine alpha, multiply it by cosine beta, I get cosine alpha times cosine beta. And if I multiply, so that's that first term, if I multiply that part times that part, I get cosine alpha times j sine beta. I have 2 more to go. So if I take j sine alpha, multiply it by this, I get j sine alpha cosine beta. And lastly, if I multiply j sine alpha times j sine beta, I get j sine alpha times j sine beta. Right. Now, let's take a critical look at this one. We have j squared times sine alpha sine beta, but j squared is equal to minus 1. So this is minus sine alpha sine beta. On top of that, if I take a look at these 2 terms here, notice that they contain a j here and a j there in common. So what I'm going to do is I'm going to take this term, which contains no j's, this last term, which contains no j's, I'm going to combine them together, and I can rewrite them in parentheses as cosine alpha cosine beta minus sine alpha sine beta. And for the second part, right here, for these terms, I can factor out the j, and I'll get cosine alpha sine beta plus sine alpha cosine beta. And this has to equal cosine alpha plus beta plus j sine alpha plus beta. Now this is the really important part, and this is the really, really cool part. Remember, on both sides of the equality here, we actually have a complex number. They're a complex number in different forms. But if they're going to be equal, then the real part of one has to equal the real part of the other, and the complex part has to equal the complex part of the other. So by this equality here, I can say, without a shadow of the doubt, that this has to equal that. And that this, in blue, that I'm underlining, has to equal that. So I get 2 conclusions. The first conclusion is that cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. And the second conclusion is that sine alpha plus beta has to equal cosine alpha sine beta plus sine alpha cosine beta. These are trigonometric identities that are used over and over and over and over. If you have ever tried to prove these using only trigonometry and geometric constructions, I'm sure you remember how much of a headache it was. This pops out completely easily and naturally with the use of complex numbers. Right? So once again, at least for me, proving that complex numbers are useful and cool.